Now in section 5.3 we deal with a different definition than before. We deal with independent, which is actually really important to us. Namely, what we want to know is, does the occurrence of an event E affect the probability of the next event F happening? Now keep in mind this is implying that there's a couple of experiment trials, one after the other. That's not the same thing as disjoint. Disjoint was I drew one card, or I pulled one person, I rolled the dice one time. What's the chances it's this or the other? And the disjoint means you can't have both at the same time. Okay? In other words, you're doing something once. But in independent, you tend to be doing things twice, 3 times, 4 times, etc. And seeing, hold on one second. There we go, I found it. All right, so you're seeing whether the first thing affects the second thing, right? And it's usually one after another, right? More than one time. So for example, I'm having a coin, that's the first thing, and then I roll a die, that's the second thing. Does the coin landing heads affect the die landing on a 5? The answer is obviously no, right? So probability doesn't work like that. Coins and dice are kind of the definition of independence, right? All right, now what about a gumball machine? So I know I had red in here originally, so that's fine. If you get a red gumball from the machine, does that affect the chances of a red gumball from the machine the next time? And the answer is yes, right? I mean, if you take a red gumball out, then you're affecting what's left in the bowl, right? So there's less red ones. And like I was writing in earlier, you could also say it's affecting the probability of a blue one. Because if you take away the red ones, right, if one more red one is gone, that means the chances of getting a blue one has gone up generally. Okay? So it would affect both probabilities. So a gumball machine is kind of the definition of dependence, right? Because what you get for the first time affects what's left in the jar for the next time. Now, what about your first child is a girl? Does that affect your probability of your second child being a girl? And the answer is no, right? For most healthy couples, first child is a girl has no bearing on whether your second child will be a girl. Now, I know genetically there are some exceptions to that rule, but for the most part in our class, we treat gender like they're independent, 50-50 shot. All right, now what about cards? If you're playing with a deck of cards and somebody deals you an ace, does that affect the chances of being dealt a king next? The answer is yes, right? I mean, being dealt an ace means there's 51 cards left in the deck, 4 of which are kings. So you've slightly incrementally increased your chance of getting a king next time because you were dealt an ace the first time. So that's dependent. If, however, you replace the card in the deck, and of course this is assuming you're choosing randomly and are not, playing against a magician or something, right? So if you're dealt an ace, then you replace it and then randomly choose, then you're dealt a king. That's independent, right? Because you put it back in, then what you drew the first time should have no bearing on what you drew the second time, as long as you're not playing against a famous card trick person. All right, now what does this mean for us? Well, this is going to affect our chances of finding independent event probabilities. So if you know E and F are independent, then you know that the probability of E and F is equal to the probability of E times the probability of F. Now, it's important to notice this only works if they're independent. If they're not independent, you have to have other ways to do it. So there are some more complicated rules in the next sections. Or, let me scroll back up here for a sec. We found it, right there. Look at that. AA and female. You already found an and probability for a contingency table. It was right here. And the way you did that was just kind of looking at it. As a matter of fact, the independent rule wouldn't work here because this table is not independent, right? These numbers are not all equal for different categories. So the chances of being AA and female was right here where the column AA and the female overlapped. So that was a way to find an and probability without actually needing this rule that we're learning now in 5.3. You also did it right here with the heart and the face. By drawing out the diagram, you're able to see, oh, there's the hearts and the faces right there. But you didn't need that rule. As a matter of fact, that rule wouldn't have worked because this is not really an independent event going on here. It's a little funky. So the rule that we're learning now in 5.3 only works if you're talking about independent events. If you're talking about other kinds of events, you either have to figure out a different way, or you have to figure it out with a different rule that we would learn in section 5.4. All right, so the following table shows the number of graduates from JCC from spring, blah, 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 blah. Okay, it's the same table we've been working with before. Now, the first thing they want is you're going to select 2 JCC graduates. You want the first one to be an AA, Associate of Arts, and the second one to be certificate. Okay, so I wrote it right here, but let me go to Excel to have me do the finding. And again, I don't really need Excel to do this. It's not like I'm just using Excel as a glorified calculator at this point, right? Okay, so I want the probability of AA and cert. That's the probability of AA times the probability of certificate. Because if I get an Associate of Arts, it has no bearing on whether you're going to get an Associate of Arts, right? So I take the probability of AA times the probability of certificate, and I multiply them, and there you go. I'll make that orange. Not really sure what's going on there. There you go. All right, now what about letter B? I want the probability of AAS, Associate Applied Sciences, and another AAS. They're both. Okay, that word both, do you see that? That's a kind of a hidden word in math, in statistics and probability. Because when you see both, what it's really implying is and. See the and right there? Because it's both first one is AAS and the second one is AAS. And that word both implies that. And you have to know that. So you might want to make a note of it somewhere. Right, so I'll put it right here. Note both means and. Okay? All right. So that means I have to have AAS in the first one, AAS in the second one. That's 4745 times 4745. Let me go over here and make Excel find it for me. It's 4745 times 4745. Now notice that you could also do that with 4745 in parentheses squared. Actually, I don't even think you need the parentheses, to be honest. So you can square it. Remember, squaring is the same as multiplying something by itself. So that can help as well. I could even say that here. I'll put it right back over here. Just for your own benefit. Is equal to There you go. Squared. Cool. All right, we're done with that one. Oh, and I better save my technology sheet because I'm getting close to when I'm going to turn it in, so I might as well make sure I've got it all. All right. Now, what if there was more than one? And the answer is you just string them along. I mean, as long as they're independent, which you got to make sure you got that. But if you have independent, you can just keep multiplying. Probably the first one times probably the second one, and so on. So suppose I was going to do 3 graduates. What's the probability that all of them are AAS? Well, I'll just do it down here. 5.3, example 3. I want the probability of AAS and AAS and AAS, right? Well, that's equal to the probability of AAS. Oops. To the 3rd power, right? Because there's 3 of them. Oops, it's not going to like me there. Hold on. I put the equal sign, and that's why. It doesn't like equal signs with all letters like that. It doesn't know what to do. All right, so that would be, now where's the AAS? Right here. To the 3rd power. 0.1068. Which hopefully is what I typed up before. All right, I'm going to save it. Go over here. Yep, 1068. Cool. And if what if there were 4? Well, you just do it again, right? 4745 to the 4th power, and so on. You know, and I'll make a note just right here. This is equal to that probability of AAS to the 3rd power, right? So you can find it by multiplying it longhand, or you can just take 0.4745 like I did to the 3rd power, right? All right, let's expand our minds a little bit and look at the 2 children examples. So suppose you're going to have 2 children in the future. What could be their genders? Assume male, only male, female, each equally likely and independent. Use male and female, right? Now, what's the probability of male, male? That's equal to the probability of male and male, right? Which is equal to the probability of male, because we assume they're independent, times, oops, hold on. there we go, probability of male, which is equal to 0.5 times 0.5, which is 0.25. And I bet I need to do it like that. There we go. And just for the sake of your sanity, I'll put these in parentheses so you can follow along better. All right, so that one's 0.25. Okay. All right, let me pause. I'm going to fill in all the rest of these. They're going to work the same way, though. All right, there we go. So I kind of cleaned it up a little bit. It's male first and male second. So that's the probability of male times the probability of male, which is 0.5 times 0.5. Now, if you want a male first and a female second, that's probability of male times the probability of female, 0.5 times 0.5, and so on. And then female male would be female first, male second, 0.5 times 0.5, and so on. Now, I know what you're thinking, but hold that thought. So I made a probability distribution for it, right? So male, female, there's the outcomes. Here are the probabilities. And I noted right here, this should look very familiar to you. We already made this. Matter of fact, I will go back and find it. Let's see, where was it? One die, one card. There it is, 2 kids. Look at that. There it is. Male, 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 female, and so on. So we did it with a tree diagram back here, and then we were like, oh, okay, so it's a 1 on 4 chance, all that good. Okay, well, what are we doing it now? What's the point? And the answer is, what we're doing is we're learning a way that's better in the long run. The tree diagram's great for very small families of only 2 kids, but what we're learning here is something that'll work even when there are really large sample spaces, right? Suppose you're having 10 kids, right? This multiplication rule will work. And it doesn't always assume equally likely. When we were doing the tree diagram, you assumed 50-50 every time. But you don't have to with this way. When you have the multiplication rule, it doesn't have to be 50-50, and it'll still work out. Okay? So this is a better way to do it than tree diagrams. Tree diagrams are nice when you're first learning, but they don't really help out too much in the long run. This method, this multiplication rule, will work all the time, even for more complicated data sets. Speaking of which, let's try to do it. So hold on one second. Okay, so let's see what happens if they're not equally likely, right? What happens if it's not a 50-50 shot? So assume for some biological reason the chances of your children will be girls is 85%. Okay, so if that's the case, and again, assume that it's independent still, but you just have girls to 85% of the time. So what's the probability of male, male? Well, that's the probability of male times the probability of male, but that's 15% times 15%, because 85% of them are girls, 15% of them are guys. That's a complement rule thing, right? They got to add up to 1. Okay, what about male, female? So you got to have a male in the first one, that's 15%, times a female in the second one, that's 85. 15 times 85 makes 1275. Again, I just used a calculator or Excel to do that. Female male is the reverse, right? 85% on the first one for female, 15% for the back one, which is male. Remember, notice their complements, they got to add up to 1. And then female female is 85 times 85, so 0.7225. And then you can use that to build a table. It's still got the same outcome possibilities, but the probabilities are all different, right? The tree diagram and this other method here, right, they didn't lead us to that. This method could lead us to that, and that's what you're seeing. That's why the multiplication rule is stronger. It helps you figure out what to do even when the probabilities are not equivalent. They're not 50-50, right? Which is not something we messed around with too much in section 5.1. When we were making those tree diagrams, we were assuming a lot of things were equally likely, but it doesn't have to be so. All right, what about a really large sample space? All right, if you're having 5 kids, that'd be 2 times 2 times 2, 5 times is 32. Nobody wants to make a tree diagram with 32 branches, right? But you don't have to. The multiplication rule means you can just multiply. 0.5 times 0.5, 5 times, and that'll get you 0.03125. If they were equally likely. If they're not equally likely, like the 85%, you just 85, 85, 85, 5 times. No need tree diagrams needed. You can just figure out the answer from that using the multiplication rule. Awesome, huh? That multiplication rule really helps out for big sample spaces like this.